In chapter 2, we deepen our theory of matrices and we'll ultimately end with talking about matrix determinants, which are useful tools for making conclusions about, among other things, the linear systems associated with matrices. We start chapter 2, though, with matrix operations, or the algebra of matrices. Basically, if we think of algebra as being the way in which mathematical objects are combined to create or yield new objects. So a matrix plus a matrix is equal to another matrix, this sort of thing. Some just general definitions are made right out of the gate here. We've got M by M matrix has, this is actually backwards. This should be n rows and m columns. And I think typically we'll actually write it as an m by n going in alphabetical order just because it flows off the tongue a little better. So we've got this matrix A, and we can denote it by its columns. We've been doing that back since chapter 1. So that's already known. We can also denote elements of a matrix in terms of their entry. So Aij is the ith row, jth column's entry. So we go down to the ith row and then we move across to the jth column, and we're talking about this element Aij. We're talking about the vectors on the top. Of course, we're gonna have that in bold, or for writing it, we'll have an arrow over the top of A to denote that it's a vector. So those are two different ways of accessing either a row or an actual entry of a matrix. Now, the diagonal entries of an n by m matrix are all the entries whose column and row number are the same. So A11, A22, A33, all the way down to ANN, or wherever that might end, AMM possibly as well. A square matrix is one with size n by n. So the number of rows is equal to the number of columns. It looks like a square more or less when you write the array down. So that's where the name more or less comes from. So next is a diagonal matrix, is a square matrix whose non-diagonal entries are 0. So anything that is not A11 through A sub n is equal to 0. So we've seen identity matrices are diagonal matrices. They have ones along their diagonal and zeros everywhere else. So, and here we reintroduce that identity matrix. I sub n has main diagonal entries equal to 1, as I just said, and we'll often denote it as, well, with this n subscript to let the reader know that this is the matrix from the identity matrix for the vector space Rn, or the real space Rn. The m by n matrix whose entries are all 0 is called the zero matrix. And the size of the zero matrix is typically inferred from context. And that's the same for the identity matrix as well. We're talking about 2 by 2 matrices, and we write down the matrix I, then we're talking about the 2 by 2 identity matrix, unless otherwise stated. So we'll get to work defining how two matrices are equal to each other. Two matrices A and B are equal, and we write A equals B. If they have the same size, in other words, they're both 2 by 2 or 4 by 7, whatever their sizes may be, they have to be equal in size, and they also will have to have corresponding columns which are equal. We could go even further than that, say they have to have entry by entry values that are equal, but both of those things are the same, because if we're looking at columns, we're comparing vector equality. We already know vector equality is entry by entry equality of two vectors. Let A and B be two m by n matrices. The sum of A and B, denoted A plus B, is another m by n matrix. It's important to note that, whose elements are obtained by adding the corresponding elements of A and B. So the same way we added vectors would be the same way that we add matrices. So in this example, they ask us to add A plus B, where we're given a matrix A and a matrix B. First, we note that both matrices are 2 by 2, so they match in size. So we can actually add them together and get a 2 by 2 matrix as a result. When we do so, it's first component yields a 5, and then so on. It's first row, second component, -1 and -1 is -2, and we could carry on and see the rest of of those entries work out as well. Second row, first column, second row, second column, and we'll be done with that one. Now, a scalar multiple of a matrix is very similar to the scalar multiple of a vector. So the scalar multiple R times A is the matrix whose columns are R times the corresponding columns in A. So matrix or scalar multiplication of a matrix is the same as scalar multiplication of a vector, but we do so for each column of the matrix. The other way of envisioning this or just dealing with this is to look at it and realize that, well, we're just going to multiply 2 by each one of these entries and get 6, -2, 0, and 10 down here. We do something similar for B, because after all, this example is asking us to compute 2a minus 3b. So we handle the constant multiples first. 3 times 2 is 6, times -1 is -3, -15, and 21, and that's this matrix right here. Then we add them together using the technique we just saw above, or the definition we just saw above, and we get this result. So scalar multiples and sums of matrices leaves us with this idea of linear combinations of matrices. And we won't really dig into that too far or deal with it, but it's interesting to note that we can look at this and see it as a linear combination of the matrices A and B, interestingly enough. So some properties of matrices. We have commutativity of addition. A plus B is equal to B plus A. We have transitivity of addition, or associativity of addition. A plus B and then add C is the same as adding B and C first and then adding A. A plus 0, this is the 0 matrix, is equal to A. R times A plus B, we can distribute scalar multiples times sums of matrices to get RA plus RB. We can distribute sums of scalars times a matrix A to get the scalar multiple of R times A plus the scalar multiple of S times A. And we have associativity of multiplication of scalars as well. We can multiply S times A and then by R, or we can multiply R times S and then multiply that scalar times A, and we'll get the same result either way. These are all fairly straightforward to prove. I have just a quick proof of part A, just to give you the idea or flavor of how these results are proven. Remember, it seems like something you would take for granted. These are properties that the real numbers have. All of them actually are properties that real numbers have. But it's interesting to note that matrices also share these properties. And in a large way, that comes from the fact that real numbers have those. It's inherited. But we will see some properties that matrices don't inherit from real numbers by the end of this section. So proving part A, we let A be the matrix Aij with subscripts Aij, or subscripts Ij, and B will denote as the matrix lowercase b with subscript Ij. So these are all the entries of A and B. This is the Ij entry of A, the Ij entry of B. For I and J ranging, I ranging from 1 to M and J ranging from 1 to N if A and B are M by N matrices. A plus B is equal to the matrix whose components are added together as Aij plus Bij. So for each position, we add each corresponding position together. Well, these are real numbers. It's the sum of two real numbers. So we know that A plus B is equal to B plus A in terms of just real numbers. So we can swap the order along this equality. And once we've got this written, we can back right out of this notation into matrix notation. This is equal to B plus A. So it is a fairly obvious result, but we don't have it for all matrices, and understanding that it has to be proven for each one of these down the line, because this is truly a new object. It's not just real numbers that we're dealing with. We're dealing with real valued matrices. Potentially later on, we'll deal with complex valued matrices. Luckily, complex numbers share most of the same properties that real numbers do in these regards. So these properties are held or maintained in that space as well. So matrix multiplication, and this is probably the more complicated operation that we'll see in this section. So let's recall that if we multiply B, a matrix, against the vector X, for which the dimensions are suitable, we end up with this image vector B of X, or B times X. We can think of that as a transformation. This matrix product transforms X to B of X, or B times X. If we take that new vector Bx and multiply it by another matrix A, again of suitable dimension, so that this product is well defined, we get yet another transformation, right? We think of it like this. Maybe we have f of g of x. We apply g to a variable x as a function, and then we apply the function f to the output of g. This is the same thing as composition of functions. And in the case of matrix multiplication, a times b times x, this expression right here, can really be thought of as a composition of mappings. So this is an example of composition that we've seen, applying a function to the output of another function. And in this case, matrix products can be thought of as composition of mappings. So let's find what such a product should look like. And what we're more interested in is leaving the x out and seeing what a times b looks like. If this in fact is a new mapping in itself, then what's the matrix of that mapping? And I think most of us would guess, well, it's probably whatever matrix a times b is. We need to figure out how to define that. So we'll view all of this through this composition of mappings idea. So we let A be an m by n matrix, B be an n by p matrix, and then we let X be a vector in the real space P, or p-dimensional real space. So we'll denote the columns of B in the usual way, bold B1 through BP. Remember, there are P columns in B here. And the entries in X by X1 through XP, that's also in the normal way. And recall that the product of the matrix B times the vector X is the linear combination of the columns of B using the entries of X as the weights corresponding to each column. So we have this linear combination as the product of B and X. Now, if we wanted to take this further, and given that A is a linear operator as a matrix product, right? Remember that linear transformations all have unique matrix representations A, and if we look at a matrix A, we can consider that to be a linear transformation. Since A is linear, we can take the following steps. We're going to apply A to this vector Bx that we've got above. Remember, a linear combination of a vector yields a vector. Some vector V comes out of this product right here, this linear combination. So then we apply A to that vector V right here. Well, V is composed of all of these terms, or this linear combination of these vectors. So A being linear, this is where we finally use that property. We can multiply A times each one of these. A times x1 b1, A times x2 b2, all the way up to A times xp bp. And that's what we have in the line below. Now we have A times the vector bx is a linear combination, x1 up through xp, of A times b1 through A times bp. So what we were able to do is use the scalar multiple property as well of this scalar x1 times, or of A times x1b. Right, so this term would have looked like this initially, ax1 b1, and this is a scalar which we can multiply. We know that A times this is a vector. A times a vector is going to yield a vector. We can factor, thanks to properties of scalar vector multiplication, x1 out into the front of this as follows. It's a subtle point, but of course it's one that really kind of needs to be accepted. But the most important fact about all of this, though, is what we end up with. We realize that this is a linear combination of the vectors a b1 through a bp. Well, that's exactly a product ab times x, right? So that motivates our definition for what a times b times x is, or a times b. I'm trying to say the the associativity of the parentheses. But so we see in the line below, we have this repackaging of this line right here. So what we have now is a new matrix. This is a new matrix right here. It consists of the columns A, B1, which is the product of the matrix A times column B1 from matrix B, all the way through the pth column, which is A times BP, which is the matrix A times the vector BP, or the column BP from the matrix B. And it builds a new vector a new matrix, and that's thanks to this linear combination statement right here. So that gives us an idea of what this transformation A times B with the new composition transformation should be defined as. It should be defined exactly in this form, and that's exactly what we do below. Right, we define the matrix product AB as A times the columns of B, and then written in a little bit one step further, more explicitly, is this last component of it, A times each column vector B1 through BP in the matrix B. So the definition matches exactly what we would expect from the composition of these two mappings, so that thinking about these matrices as linear transformations guided our decision on how to define matrix multiplication. I think this is a really nice way to think about matrix multiplication. It's often taught without, or at least learned without connecting it to any transformation idea. So it's this disconnected idea of how to multiply two arrays of numbers with no meaning behind it. In our case, we see that a matrix product is a composition of mappings, which is a really it's got a strong connection to practical use. So always think of matrix products now as a composition of mappings, and it'll give us some background into how useful they are and what they actually do. So let's see, we're asked to determine A times B. If we have the matrix A given as this, note it's a 2 by 2, and a matrix B given here, which is a 2 by 3, 2 rows, 3 columns. So one check to always make, and we did this with vectors previously in chapter 1, is to look at the dimensions. I mentioned that A is 2 by 2, and I mentioned that B is 2 by 3. If the inner dimensions match, it means that these two columns here will match the number of rows that are here. So imagine we're going to try to take A times one of the vectors of this, or one of the column vectors of this matrix B, right? So if we have a 2 by 2 matrix over here, and we have a something by 1 submatrix, we might call it, or vector, right? Something by 1 over here. It's got to match, right? We've got to have a 2 by 2. A 2 by 2 has got to be multiplied against the 2 by 1 if we're going to do matrix vector products. And that works out in this case. But a nice, quick, clean way to check these in the future is to look at the inner dimensions of two proposed products of matrices. If they match, we're all set, and we can multiply these two matrices. And in fact, we can go a little further and realize that the dimension of the resulting matrix is the outer dimensions. As we list these things together, we're doing A times B, so we do 2 by 2 against 2 by 3, and it'll yield a 2 by 3, and that's because of these outer dimensions. So we think about the inner dimensions as sort of canceling together or annihilating one another in the size comparisons. So in order to carry out the multiplication as defined on the previous page, remember that we're going to do A times B as A times each of the columns of B. So this is A here times B1. Second entry of this matrix is going to be A times B2. And the third entry will be A times B3, the third column of B. And this is a nice way to extend our matrix vector multiplication from the last chapter into this chapter. You'll find that once you make these matrix vector product calculations, you'll end up with this 2 by 3 matrix. again, that confirms what we saw above. We expected to get a 2 by 3 out of this thanks to our size analysis before we started. So always carry out this to make sure that the product is even at all defined before you start trying to do the work. What you should see is if you do start to try to do the work and you realize that there are maybe the matrix B has 3 rows instead of 2 rows, then when you try to multiply this matrix times each of these vectors, it's undefined, right? We have 1 times 2, then 3 times 3, but then what is multiplied by this extra number down here? It doesn't, there's nothing to multiply against. It would be an undefined matrix vector product. So remember, that's the number of rows here matching the number of columns. So columns of A, rows of B. That's why those numbers have to match. So down at the bottom, we get a nice useful fact, which should be obvious by now, at least after seeing this one example, or maybe a few more. Each column of AB is a linear column combination of the columns of A using weights from the corresponding column of B. That's really given by this right here. Remember that matrix multiplication of a vector is a linear combination of the columns of A with weights given by the vector that the matrix is multiplied by. So that's just reiterating an important fact about the definition there. So we're given that A is a 3 by 2 matrix and B is a 4 by 3 matrix. Which products AB or BA exists and what size is the resulting product matrix? Well, let's try A times B. We write that down. We see it's a 3 by 2 times a 4 by 3. The problem we run into, 2 and 4 are not equal. So if you write down a 3 by 2 matrix, anything will do. Put any numbers you like in it, and then put it against or adjacent to a 4 by 3 matrix as if you're going to carry out a product, and you'll realize that's, of course, if you write it in this order, you'll realize that if you try to do the linear combination or the matrix vector product of A against the columns of B, the matrix vector products will not be defined. So, or in general, from here forward, we just match the inner dimensions. If they match up, it's well defined. If not, we just state that it's undefined. B times A, 4 by 3 times a 3 by 2. In this case, when we flip it around, the inner dimensions match up, and we end up getting a 4 by 2, the outer dimensions, result matrix or product matrix. Okay, so that's a nice general look at, or more general look at, how these things are analyzed. So we have another rule for computing AB. Perhaps we don't always want to think about and write down this much intensive work here, right? To write the matrix A so many times against the vector. We can see it, we can view it as this column or this row times this column is this entry. This row times this column is this entry. So think about it this way, I'll say again, first row, first column is first row, first column entry of the result. Then first row, or sorry, second row, first column is second row, first column of the result. Get rid of these asterisks here, are not useful anymore. We've got second row, or sorry, first row, second column gives us our first row, second column entry. So I think this pretty well sets us up for how these products are carried out. Right, we can see that happening here. We're going to end up with the same result, right? We have 1 times 2 plus 3 times 3, we get an 11. We can carry on this 11. We've got second row, first column, and we'll end up with 4 times 2 is 8. 8 and 5 times 3 is 8 plus 15 is 23. Go back and check on the previous matrix. We have 11, 23. We see that this is working out, and we're going to end up with the exact same matrix. So I'll leave this as an exercise for students to calculate the rest of these in a similar fashion. So the row and column position in the result matrix is given by the row of the first matrix times whichever column of the second matrix we're looking for it to establish. So that's maybe a more efficient way to calculate these, and it's the more common way to learn matrix multiplication. But again, thinking about it in terms of these linear combinations of matrix columns and matrix vector multiplication. It really keeps everything in context for us and allows a deeper understanding of what we're doing with these products. So matrix multiplication has some interesting properties, and it lacks at least one interesting property. So associativity it has, so we can, if we have a product of three matrices, we can group them in whichever order we prefer. We're not moving them, right? But we can carry out their products in the same configuration. In other words, A, B, C, we don't change that order, but we can multiply B times C first and then A times that result, or we can multiply A times B first and then C times that result, and we'll end up with the same matrix. Those two things will be equal. Okay, we have the distributive property for matrix multiplication, as we see here. We have the distributive property on the other side of this matrix A. So we can distribute A into a sum B plus C from the left, or we can distribute it in from the right. And as long as matrix dimensions all hold here, then this will all work out to be equal. The scalar multiple of a matrix product can be calculated by the scalar multiple times one matrix, and then the resulting matrix product would be, or vice versa. R can be times B, and then we carry out A times RB. The identity matrix IM is equal, or times A is equal to A, as we would expect, and A times IM as well as A. So the identity matrix conserves the matrix it's multiplied by. Just like 1 times any real number, it leaves you with that real number. Now, the property that matrix multiplication doesn't have is commutativity. We cannot swap the order of A, B, and BA. Now remember that we saw just previously that it might not even exist, right? In one case, B times A, this matrix existed, it was well defined as a product. This one's undefined, it doesn't even exist. So we can't even think about comparing whether or not they're equal because one of them doesn't even exist. So if we're dealing with a situation where we have square matrices, A and B, it's still not necessarily true that A times B is equal to B times A. And if we carry out the two products that we're asked to look at here, calculate A times B and B times A, as the problem says, for these given matrices, then we'll realize that A times B gives us this matrix, yet B times A gives us this matrix. They're both defined, and they're both 2 by 2 matrices, so they're comparable objects. However, by the time you calculate this matrix and then the first element of this matrix product, you realize that they're not equal. This 7 does not match this 2, and these two matrices just aren't equal. So we have an example that shows that A times B is not equal to B times A. So it is generally true. So it's true that matrices are not generally commutative. Okay, that doesn't mean, that means that we cannot assume that two matrices of the same dimension will have a commutative product. There are matrices which are commutative. They do exist. This claim here is not saying that there are none, or that there are no matrices that are commutative, but it just says that generally it's not the case. And we see clearly, thanks to this example, or we'll call it a counterexample even, that no, by saying that they're generally not commutative, we're saying that there are matrices which are not commutative, and these matrices are not. An example of a matrix which is commutative, in case you're just curious about that, would be, this is maybe a little bit kind of boring, but the identity matrix times A, remember, was equal to A, and well, A times the identity matrix was also equal to A. So here's a commutative property, or here's a commutative pair of matrices, right? I2 times A is equal to A times I2. We're able to commute the matrix A around the identity matrix. Similarly, we could do that with a zero matrix. 0A is equal to A0, or A, or 0 is the zero matrix for whatever size matrix A is. They would be square, of course, so that way they're well defined in their products. So both of those are trivial. There are even non-trivial matrices that do commute, but they're a special class of matrices on their own, and generally commutativity does not hold. So always be on the lookout for a situation where that you might assume that matrix products are commutative, and it could lead you into a possible mistake. So extending the notion of products of matrices, we have a notation for multiple products of matrices. So if we have an n by n matrix, we can use power notation to say that, just as we always have, a squared is a times itself twice, right? Or a times a. And then a cubed is 3 multiples of a, and a to the k is k multiples of a. So we can multiply a matrix by itself as many times as we like. This is really similar to, by the way, back in calculus, if we thought about f of f of f, and then maybe there are k of these, all the way down to, f of x, however many parentheses should go there. We could apply a function to itself over and over. You know, if f is something like the square root function, we could put a number in a calculator and just push the square root button over and over. We're composing square root of square root of square root of whatever our number was. So that's an interesting thought there. And when we put this in light of composition of mappings, we can transform and transform and transform through the matrix A as many times as we like. And we'll definitely see some use of these powers of matrices by the end of the course. The transpose of a matrix. This is sort of rewriting the matrix with its rows as columns and its columns as rows. If we look at the notation, it tells us that the element, so the transpose of the matrix A, if we use this index notation, Aij, is equal to Aji. So now we take the value that was in the ij position, row I, column j, and we write it now, or we assign it to the value that's in the jth row and ith column. So we sort of swap its positions around since a diagonal. But let's look at this in an example. It'll be a little bit easier than just talking about the general version of it. So B is equal to this matrix, a 3 by 3. And we're asked to find B transpose. So B transpose is, we see 1, 3, negative 4. It's now written as the column. So A11 in the transpose becomes A11. That wasn't really that interesting, right? But let's see. A12, row 1, column 2 in the transpose is assigned to be the value A21. So that is second row, first column, which is the negative 1, and we see that that's what we've written here. B13, this position is B31. This is B31, row 3, column 1. So we see how things have changed from row to column. Now notice the diagonal's fixed. That's because B11 is B11 and B22 is B22 and B33 is B33, right? So all of that matches, and that would be true all the way down the diagonal, of course. But along the diagonal, we flip. Things are swapped over. So that's the transpose of a matrix. It's pretty easy to see once you deal with it a little bit. The notation, this notation is useful for proving things about it. So it's nice to get used to that more or less. But really, in all practical senses, this example should suffice for most work with transposes. Now it turns out that if we transpose B again, we swap its rows into columns and columns into rows, then we're going to get the original matrix. I think that should be obvious. You could probably confirm it by taking the transpose of B transpose in case you have any doubts about that, and at least give yourself an example that confirms this claim. Now, if you use this notation above, you could prove this result pretty nicely, and that would look like this. So we could say that A transpose is equal to, let's see, we know that this is, we'll write it in this notation, Aij transpose. We know that Aij transpose is Aj, and we're transposing it, so that's equal to Aij, and that's, well, just A. We use that element notation with the braces telling us that we're dealing with a matrix A. So yeah, transposing the transpose gives us the original matrix. More interestingly, and maybe a little bit more involved to sketch a proof for, or to actually write the proof for, is that the sum of, or the transpose of the sum of two matrices is the sum of the transpose. So the transpose of the sum is equal to the sum of the transposes. So a nice fact, one that follows thanks to the linear nature of matrices and the transpose. For any scalar r times a, and then transpose is the same as multiplying r times a transpose. And then more interestingly is probably this: AB transpose is equal to A transpose B transpose. So the transpose of a matrix product is the product of the transposes in reverse. This is actually, this looks wrong. This is wrong. This should be B transpose A transpose. Okay, and let's think about why that might be the case for this to be well defined. A matrix transpose can be applied to any matrices of any dimensions as long as, and for a product, as long as these products are well defined, that's okay. So let's think about this in this light. Now let's say A is a 3x2 and B is a 2x5, right? And we're going to talk about A times B, right? So then AB has inner dimensions go away to give us a 3x5. Okay, so we should get a 3x5 matrix. If we're going to transpose it, let's go a little further, then we're going to have a 5x3, right? Because we're going to switch rows with columns, so the size of the matrix is going to change, right? We're going to have, if we had 3 rows and 5 columns, the transpose is going to have 5 rows and 3 columns. It's just the way that works out. Now, if we're going to multiply B transpose times A transpose, well, let's look at those dimensions. A transpose is 2x3, B transpose is 5x2. The original thing that was written here isn't even defined, right? 2x3 times a 5x2, A transpose times B transpose, is an undefined object. The only way this product works out is B transpose times A transpose, because that puts things in correct order. B transpose A transpose, we get a 5x2 times a 2x3, and we'll of course get out exactly what we expected, 5x3. So that's not a proof of this equality here, but it, at least by the size analysis of things, lets us confirm that we've got the right statement. All right, let's just see a bit more deeply the correction of the typo that I just made, and it gives us an understanding of what's going on with these things. So let's look at some interesting products of A and a vector X. This will be our last example and the conclusion to this section. So we've already seen matrix vector multiplication. We have A, a 2x2, times the vector X, which is a 2x1, 2 rows, 1 column. The result of this should be a 2x1, right? 2x2 times 2x1, inner dimensions fall out. We should end up with a 2x1. And that's exactly what we see here. We get 8, 11. Remember, it's this row times the vector to get 0 plus 4, or 2 times 4. We get 8. And then second row, first column, we get -1 plus 12, and we get 11. Now, that's not any surprise, but maybe more interestingly, we can transpose a vector. X transpose is the vector. So if this was a 2x1 vector initially, X transpose is a 1x2 vector now, 1 row, 2 columns. So 1x2 times a 2x2 is still well defined. A 1x2 times a 2x2 should give us a 1x2. And that's exactly what we see coming out of the product of this, but the product for this one is done this way. We take the first row times the first column. That's 0, 1 times 0 minus 1 times 4. You get -4. Or 4 times -1, I guess. And then first row, second column, we get 1 times 2 plus 4 times 3, and that's 14. So first row, second column. Well, there's only 1 row, so we're done after that. So the result of that is a 1x2 versus a 2x1. Now, even more interestingly, we can do X transpose times A times X. Let's put all the dimensions here together as well. Maybe I'll note the size of this situation. This was a, X was initially a 2 by 1, but its transpose is 1 by 2 times a 2 by 2. Inner dimensions match. So what we end up with is a 1 by 2 thanks to the outer dimensions. And that's what we saw. Now this is a 1 by 2 X transpose times a 2 by 2 times a 2 by 1. All inner dimensions match here and here. So we know we have a well-defined product. Interestingly enough, all the inner dimensions annihilate or are just dropped out in this, and we end up with a 1 by 1. So that's an interesting fact. That's a scalar, right? We can think of it as a special case of matrices, but probably just more practically, it's just a scalar. So we should see this turn into a scalar. Well, moreover, we know that these products are associative. So we can do the first one. We can do X transpose times A and then take the result of that times X. We've got to do one of these in some order, but it turns out it doesn't matter which order we use. We could go this way as well. Since we already know what X transpose times A is from above, -4, 14, we can just write that down. This is X transpose times A, and then times the vector X, which was given, 1, 4, and then we just see this is just the dot product. If anybody's familiar with that, this is the dot product of this vector and this vector, entry by entry, right? -4 times 1 gives us -4 plus 14 times 4, first row, second column. I guess this is, I don't have to do it as rows, right? It's all just done in one shot. And we end up with the value of 52. So size analysis, I recommend all the time for products, especially multiple products, if we're not sure if they even exist or if we're writing a statement that makes sense. And it's also a nice way to check your answer, maybe ahead of time, to know what to expect for an answer, what dimension it should be, and also to catch yourself in an error if that doesn't match in the end. So that's it for section 2.1. In section 2.2, we'll start talking about matrix inverses.